Ladies and gentlemen, scientists, we are going to start. I mean, they don't even listen to me, you know. Nobody's listening to me. Bill Collis, it's time to start, although I will miss the lunch. We are going to skip the lunch, I think.
They are having some technical
Problems?
difficulties.
It's not like ICCF 24, the technical side.
The rest will be written, you know.
It's really written. There are too many consonants. Okay, now we're going to resume. It's the second part of this morning session. And Natalia, I can't pronounce her last name, so I just say Natalia is going to talk now.
Good morning, everyone. I hope you can hear me. My name is Natalia, and I represent the University of Szczecin. I came here to show you the results from the project that we are involved in, and this is Clean HME project that is funded by European Union. Okay. I would like to speak today about the overview of the scientific work that have been done for many, many years. This subject is being studied for over 25 years. We study the electron screening effect, which is important, especially for the targets that are being made of metal. So this screening effect have been studied for many different targets, including gases, insulators, metallic targets, and as well some of the alloys that we had. And it is important that for the cold fusion society, these metallic structures that are being loaded with hydrogen are very, very important for energy production. So they can actually show much larger probability for a nuclear reaction to occur. And this is governed by the so-called electron screening effect, which causes an exponential-like enhancement of the nuclear reaction cross-section. As I mentioned, there are many different targets that can be studied, but this effect is the most important or the strongest in the metallic targets because of the fact that there are free electrons there that can that allow the two fusing nucleons to overcome easily the Coulomb barrier, the Coulomb repulsion between the two reacting nuclei. The probability of the tunnel transition is greater, and this means that the cross-section, especially at very low energies, is enhanced. So it is less steep, as you will see in a second. And this enhanced electron screening effect have been shown for the first time in 1998 by Professor Strzeski group and Professor Kasagi independently. So today I would like to show you the overview, some interesting results that were shown by different authors. And I would like to show you also our experimental data that are fairly new. And I would like to compare what is known from the point of view of experiments to the facts that we know, or to the predictions that we know from theory. There is the electron screening effect is mainly governed by so-called penetration factor, and this is because two nuclei that should have this common reaction have to overcome the repulsion that is between them. Okay, so this is not very probable, but it can happen. And it can happen because of the tunnel effect. So this penetration factor through the Coulomb barrier is something that is very, very important. And you can see over here the cross-section for a specific nuclear reaction. Okay, this is the cross-section. As you see, it steeply goes down for very, very low energies. And this decrease can be slowed down if we take into account the screening effect. This screening effect comes from interpretation of the electrostatic potential between the two nuclei with so-called screening function. And then we can define so-called screening effect, which is the factor by which the screening barrier, the Coulomb barrier, sorry, is reduced. Okay, so this is the penetration factor, how it shows after we include this. Sorry, this is before we include this screening potential, and this is when we include the screening potential in the penetration factor. So it shows like with the dotted line over here, we can see the overall shape of the electrostatic potential, but if we include the screening, it is reduced due to the electron cloud that is being formed around the nuclei that are having this reaction. So the cross-section without the screening and with the screening is shown over here. We usually define the cross-section with this specific S factor, which is an astrophysical S factor that takes into account many nuclear physical phenomena. As I already told you, this research is very long now. It is over 25 years, and it has started to be implemented in nuclear physics for nuclear reactions in dense astrophysical plasma. So in these reactions, the cross-sections can be enhanced by many orders of magnitude. So this is the first work that was very, very interesting and took into account this electron screening. Then for laboratory investigations, so people started to think, okay, if such reactions can occur in gas giant planets or whatever else, then maybe we can study those in laboratory investigations. And first there was this theoretical description of Assenbaum, and then first experimental observations in gases. After that, there were the first investigation of Professor Czerski and Professor Kasagi independently, showing that this effect is really, really strong inside of metallic lattice. Okay, so the metals came here as the strongest, as the ones that will give the strongest effect of this electron screening. And these two were already shown by Conrad, so I will not go into details. I just want to show you that if we take into account our group experimental data from high vacuum experiments, there is a huge discrepancy between the theoretical predictions. Conrad already explained how these predictions were performed. However, you can see that there is huge difference, at least a factor of 2 or 4, sometimes even larger than that, between the theory and experiments. So this allowed for the very, very extensive studies. So many different laboratories, many different people studied many different materials, and you can see a plot over here showing very different materials that were studied. This is the screening energy versus the charge. So if we take, for example, palladium, we can see that we have values of about 800, but also 600, and even 300 or, and something. Okay, so there are diverse informations about specific type of metallic environment. So even a single kind of target can be interpreted in many different ways. And actually there is a lot of data out there, and it's very hard to distinguish and to interpret them because of some systematic errors that were done during the experiments, because of different techniques that were used, different analysis methods, so there are really huge differences even in the experimental results. We think that they come mainly from the contaminations, but also from the neutron density that was sometimes not stable in this metallic target. And we also suppose now that these contaminations can actually cause some damage to the crystal structure, which is sometimes good and sometimes bad. And when it is good or bad, we don't know that yet. So here I would like to show some of the interesting results for DD fusion, so deuterons plus deuterons. I would like to show some of the extraordinary high values, okay? We don't definitely agree with all of the values, okay? We think that there might have been some mistakes. So these are the papers from which I took those data over here, okay? So we have palladium, which amounts for the electron screening energy of 800 electron volts. We will have Matej later on also explaining his work on palladium, so we will see what's there. The theoretical value for palladium is about, I don't remember exactly, 135 or something. So it's far, the experimental value is far from the theoretical one. Okay, and you see others, okay, I don't know the English names, sorry for some of them. So yeah, rhodium, okay, antimony, rhenium, platinum, and cobalt, and so on. You see, so there are a lot of them that have this high electron screening energy values that were reported. But we think that these systematic errors and diverse techniques actually provided this high screening energies, but we think that they are exaggerated. Okay, so nowadays when we really care about contaminations and our experimental setup, these high values are not showing up in our experiments. Okay, okay, and data acquisition and data analysis are affected generally by formation of surface contamination layers. So these are carbon layers and oxide layers. Hydrogen density in studied environments can change, so it depends strongly, also the value that we get depends strongly on the amount of deuterons that we actually got in the target. And understanding of nuclear and solid state processes also is important to interpret the data correctly. Okay, and there have been some other experiments. I call it here the heavier nuclei experiments. So you can see an experiment on lithium with deuterons or lithium with protons. Okay, so the two kind of reactions, I have here 6 and 7 because in natural lithium there are the two isotopes involved. So the first material was palladium. This was done by Kasagi with the deuteron beam. and the value arose to 1,500 electron volts. So this is crazy high, let's say. Okay, but these experiments were really well described in the paper. Okay, again, the paper is given over here. Then we had lithium target, and again, this was the proton beam reaction, so this is this one. And the value, depending on the fact whether this was a lithium-6 or a lithium-7, was different. And they also did the same kind of reaction with the proton beam on palladium-lithium alloy. There was only a small amount of lithium in palladium, and the values are even higher than that. I want to mention that Kasagi, in his paper, wrote that the enhancement in palladium cannot be explained by electron screening alone, but it suggests the existence of an additional and important mechanism in metals. So we agree with that, but maybe there is another understanding of what we think about that and what he does. We think that actually the formation of defects, of vacancies, can help, but how much there should be of these contaminations, let's say, we don't know now. So we need to figure that out. Okay, and there is some more data from Matej Lipoglausek that will speak just after me. This is the work from 2010, and they have the screening energies, and I want to point it out. This is in kilo electron volt, okay? So the screening energies are also very, very high from, in comparison to our results. And again, palladium gives 1.9 kilo electron volt, and there is this additional alloy with silver, and it gives 2.8. Okay, and Matej explained that large electron screening was only visible when foils were under tensile stress. And another work of Alexandra, which is with the date 2015, and also different targets studied with the inverse kinematics. So they have like fluorine beam or boron and lithium beams, and different targets in which the deuterons are embedded already. So again, the values of electron screening depend on the kind of beam that were used and the kind of material in which it was studied. So the highest value is over here. This is 115, again in kilo electron volts for a graphite target. Okay, there were also other experiments concerning electron screening effect, because people thought that if the electron screening effect can change the nuclear reaction rates, that maybe this is also possible to change the decay constant, or the lifetime, let's say, not the decay constant, the lifetime of a specific radioactive nucleus if we embed it in metal and lower the temperature to some room temperatures. These claims were actually based on the Debye-Huckel model of weakly coupled plasma, which is not the case if we want to interpret the metallic target that is here the host material, okay? Because in metals, we have the free electrons, they move very fast, and we need to include quantum effects, and that Debye-Huckel model was based on a classical approach, okay? So it didn't take into account any quantum effects. So the basis of this assumption was already not so good. This can apply to alpha and beta plus decay, and this is the result of one of the experiments that were done in Canada, I suppose, or yeah, Vancouver, I think, maybe I'm wrong, by Götz Ruprecht. This is the reference for that. And it was sodium-22 that was hosted in aluminium The screening energy at room temperature is estimated by multiplying DD screening value for aluminium by the charge number of the sodium, so sodium daughter nucleus, sorry. And there was a 2% increase expected in beta decay, according to this paper, because I spoke later to Konrad and he told me that these calculations might not be that precise. But according to this paper, it was supposed to be 2% change in the lifetime, and they arrived at 0.2%. While cooling, oh, sorry, this is not Gutt's paper. They arrived at 0.45. Now I think that this is wrong. Okay, it might have been 0.7. Sorry, I don't remember. While cooling to 90 Kelvin. And there was another group working on that, Limata et al. And these people found 0.2% while cooling to 12 Kelvin. So there was not that much of a difference, which suggests that this approach is not correct. And knowing that all of the people are studying different materials with very different techniques and in different environments, we really wanted to focus on the best conditions in which that kind of reactions should be studied. So, okay, thank you. So at the University of Szczecin, we now have the accelerator that is built directly for low energy nuclear reactions, for light nuclei, so we study DD reaction on our everyday basis. We have the electron cyclotron ion source, we have the acceleration beam with some lenses and the analyzing magnet. The beam is impinging on a target. This target is a metallic target. Firstly, we implant the deuterons in the target, and then we run the DD reaction and check what are the charged products of such a reaction with the detectors that are being protected from scattered deuterons with aluminum foils. We have silicon detector, usually one, but sometimes more than that. Okay, and we have ultra-high vacuum. I will skip this part because this is our full data acquisition and analysis method, which is complicated. I just want to show you that this is how our spectra look like from the regular, let's say, in the field of electron screening, from the regular formula, we calculate something that is called reduced yield, and this is in comparison of what we have experimentally to what we would have if this reaction would have taken place without this metallic environment, okay? So for bare nuclei case. So with that, we have that kind of graphs that you see over here. We have few counts over here, few counts over here, and few counts over here. And we manage to say what kind of differences there are between the different energies studied, okay? So then these that are being called enhancement factors are being plotted in a plot like this, and then we can use the function to check what is the screening energy. And because we want to check the conditions for very different metallic targets and alloys, we would like to have a very fast and quick data analysis. So we introduced this new data analysis in which we have the ratio between enhancement and counting rates at two different deuteron energies. One of them is the energy that we use for the monitor measurement, and the other one is the studied energy. And considering this new data analysis, we have used it to analyze the data of latest experiments. And we used, again, deuterated zirconium target, and we arrived at the value of 100 electron volts, while the theoretical value is 109. So this high zirconium value that was about 300 is now quite quite close to the theoretical one. We also used nickel-beryllium deuterated target, and we got a good result, 450 electron volts. Unfortunately, the Mathe's group also studied that, and they had not good informations for us. They didn't reach that high values. Nickel-lithium deuterated target, again, around 300 electron volts, and nickel-lithium clean target with lithium P-alpha reaction. And these, unfortunately, had too low statistics to say anything about the results, so I'm not even sure if we will take a look on that again. Okay, and to be honest, because we really think that now we understand with our theory and our understanding of the processes that are involved, that we really do understand what is happening with the screening. So for zirconium, we have good values experimentally that agree with theoretical values. And we know that sometimes the screening energies are much, much higher. So we think that the reason for that is the amount of impurities, of vacancies, of crystal lattice defects that are there due to the beam irradiation in this metallic target in which we study the DD reactions. So for this reason, we applied positron annihilation spectroscopy, and maybe I will skip that, and I will only advertise that Mathieu will talk about this tomorrow at 9:30 if the schedule won't change. Okay, so I will go to my conclusions. So we have experimental results showing very high electron screening energies, but we think that some of them are too optimistic. We have at our University of Szczecin, at the Elbrus lab, we have determined usefulness of targets like zirconium, nickel beryllium, and nickel lithium for cold fusion studies. We implemented new method for quick estimation of this enhancement, and with that method, experimentally measured zirconium target screening energy agrees with the theoretical predictions. Cross sections can be enhanced due to crystal lattice defects, and this results in larger effective electron mass. So we should implement the bulk and surface analysis into further studies. And clean target and very contaminated target will show us the low screening. Slight contaminations will increase the screening energy. So we think that in the future, if we know which amount of contamination is good, we can actually control the number of crystal lattice and then manipulate the cross section. Okay, thank you very much.
Very good, excellent. Thank you very much. I mean, we never do experiments in ultra-high vacuum when we do electrolysis and the gas, so there are always contaminations. Anyway, any questions?
What's the percentage of lithium in your lithium-nickel target? What is the alloy composition?
Okay, I shouldn't talk about that because this is consortium confidential, and that's why the data were not put here.
Okay. It's good, looks like a secret, you know. Any other question?
Sorry, maybe next year.
Secret sauce.
I have a question. I mean, we have shown that when you have an oxide on top of the metal, that increases the reaction rate. So did you try palladium oxide to see what happens?
No, not yet. We tried to do some contaminations with carbon. Yeah. We are a bit afraid of oxides in the ultra-high vacuum system, you know, because there is very hard to get rid of them sometimes.
No, you just oxidize the nickel, the palladium, by heating the palladium in low pressure oxygen. and that will be enough. And then you will have an oxide layer, because I published with 2 other people a paper showing that excess heat occurs always when you have an oxide layer.
Okay.
So you should look at that.
So yeah, from our experiments, we see that oxide layers actually destroy the screening effect. So I mean, we couldn't control the amount, you know, so we are not sure how much there was. Maybe it was enough to stop everything, and maybe a little more would help. So this is something that can be investigated.
Okay, I think we have to continue because I am the chairman
Thank
here.
you.
So thank you very much, Natalia. It was very good work. Our next speaker is who? I don't know. Who's our next speaker? Mathieu. Mattei. Well, in français, we say Mathieu. Anyway.
Yeah,
Mattei, Electron Screening in Palladium.
Yeah.
Good.
Thanks. So I'm grateful to Rakesh, Konrad, and Natalia for this nice introduction. So I will skip the introduction so I can just talk about the results. Okay, yeah. So I will talk about nuclear reactions, low energy nuclear reactions. So I need to define a few terms that I will refer to. So the first one is what is the kinematics of the nuclear reaction. The normal kinematics is when you shoot a light particle on a heavy target. And inverse kinematics is when you shoot a heavy particle on a light target. In principle, the outcome of the reaction should be the same. The only thing you need to worry about is that you keep the energy in the center of mass system the same. So even though this will be low energy nuclear reactions, then in inverse kinematics, this can amount to a high energy of the beam, but still in the center of mass, it's low energy. So for example, with fluorine beam, in inverse kinematics, we shoot like 6 MeV, and we get 300 keV in center of mass with reactions on protons. So the whole point is low energy nuclear reactions, they happen with tunneling. The reactants, the charged particles have to tunnel through the barrier, and this was already introduced, how this tunneling goes, so I can skip this. I want to point out this paper from 1950s. This is actually cold fusion. Even though Bill said yesterday that this was hot fusion, it's not. The point is with hot fusion, with this reaction with protons and deuterons, you get a gamma ray and helium-3. In this case, when muons catalyze the fusion reaction, you get muons instead of gamma rays. So the muon takes away all the energy in this reaction. I mean, it's a bad picture, but you see the muon track here. Muon and then helium-3. So the outcome of the reaction is different. So electron screening, this was also nicely introduced. Langanke in '87 put this picture of electron screening. This is now a classic picture of electron screening. Unfortunately, it doesn't work. So the picture is you put all your electrons at the atomic radius. They make a charged sphere. Inside this charged sphere, you have a constant potential. that you can then deduce from the Coulomb barrier. And then this is the same as increasing your particle energy by the same amount, the constant. And this constant is called electron screening potential. But this is not really, it's just mathematically you get the same result. Unfortunately, this gives you very precise predictions of what the electron screening potential should be. And for, let's say, deuteron plus deuteron reaction, you get 27 electron volts. And you heard already in the previous talks, this is too low for what we see. Oh yeah, and another point is that, you know, this picture also works inside the nucleus. So actually the protons are bound more inside the nucleus than what they would be without those electrons. So this also needs to be taken into account. So Klaus Rolfs and his group, they measured all metals, and they always got electron screening potential, not always, but in many cases they got electron screening potentials that are higher, much higher than this prediction of 27 electron volts. The highest one, as Natalia said, was measured in palladium, 800 electron volts. At about the same time, the Kasagi's group from Japan produced very similar results. The interesting point here was that the highest screening was measured in palladium oxide. They measured like 600 electron volts, and palladium oxide is an insulator, so it seems that this effect, large electron screening, is not limited to metals only. This is an insulator. Yeah, the other two results were fairly old. This one is fairly new, but Konrad talked about it a lot, so I will not repeat it. Yeah, Natalia mentioned this one as well. So yeah, they tried to go to heavier beams or heavier targets. This one is with lithium target, and by the Bochum group, and they measured quite high electron screening potential in palladium lithium target. This what I think is important. Lithium was implanted into palladium by plasma discharge. You should not forget about it. And they got 3.7 kilo electron volts for this reaction with lithium. They also went on to measure higher Z beams or targets, but some of those papers are completely wrong. So I spent 3 years trying to repeat those, and don't try. Yeah, another paper from Catania. Again, they were with the same reaction quite above the adiabatic limit. The picture of Langanke, what I was referring to, is also called adiabatic limit. They also tried to study temperature dependence of electron screening potential. This is for titanium, which at room temperature had very low electron screening, but then when they increase the temperature, and then the solubility changes, and they got then a high electron screening potential of about 300 electron volts. But this is not directly related to temperature, but to changes in the structure of titanium and hydrogen in titanium when you increase the temperature. So this is just somehow coincidence with temperature. So it's not directly temperature related. But okay, you can see that already here. There are differences in the same target depending what you do with it. So this is now a picture of our accelerator. We have a 2 megavolt tandem accelerator with which we can produce almost any beam that we want. And we are proud of having intense proton beams, and we also produce helium-3 beams, which are quite expensive. But we have some way of saving helium-3 so that we don't use 10,000 euro bottle per day. So, yeah, this is it. So that's our target chamber. Since the cross sections that we want to measure are very low, we try to push our detectors as close as possible to the target, which sits on this wheel. We can have, this is a silicon detector, behind it a germanium detector, then we can put a neutron detector. This is an X-ray detector, so we have all sorts of detectors that we can detect the particles with. And this was also mentioned yesterday, the Tectra ion gun, which we use to implant into various targets. We implanted 3.5 kilovolts. And what was not mentioned yesterday, we know that this ion gun, it's a microwave plasma ion gun, it produces mostly H3 plus ions. Then there is some H2 plus and also some protons as well, or deuterium, whatever you put. So this is what we use to implant, and the outcome of the implantation is already, can be seen here. This is the gamma ray energy of this reaction, protons plus deuterons. We get the gamma ray, and the shape of the gamma ray already tells you the distribution of your deuterium in the target, which is important for further analysis. So this one, in this case, all the deuterium was, or most of the deuterium was on the surface, and this one was in the bulk. So you could see the cross section all the way down to zero energy. Another way to get hydrogen or deuterium into the target is with palladium. We can just put it in the gas, and if you have a good palladium, this is what comes out. You put it in completely flat, and then yeah, it absorbs 70% of atomic percent of hydrogen, and it's all deformed, squashed, and difficult then to measure, but that's what you get. So at room temperature and 1 atmosphere, you get 70% of hydrogen per palladium atom. And then we can weigh this, and weighing it determines pretty much very well how much you have in, how much hydrogen is in. And then during the Corona times, we had plenty of time because you know, we couldn't go anywhere, we couldn't travel, so we had time to do what I call cycling. So you load hydrogen into palladium, then heat it up to 300 degrees, then it's empty, and you repeat this cycle day by day. So after 20 days, you know, it's still the same. So we were quite happy that in this case we know how much hydrogen is in our palladium foil. So this was what I call hard palladium. I will tell you how it is made. And this one, instead of 70%, had always 46, 47% of hydrogen in palladium. So then we have more time. We had more time during Corona. So we had two palladium foils. One was hard, meaning we asked the manufacturer to really cold roll it from about 2.5 millimeters to 100 microns in several steps, but then that's what we got. So this hard palladium had less hydrogen and it lost it more quickly. So if you look at the time scale, it's in days. So every day we weighed this palladium and we determined how much hydrogen is in. So the other foil was a soft one. So you could really turn it, squeeze it, whatever you wanted. We bought it just off the shelf from Kempur, and it was soft. So they already, here you see that they behave differently. Then we studied this nuclear reaction. We set on this resonance. This is protons on fluorine target, and you get an alpha particle, but we measure this oxygen-16 gamma ray, which is here, a very clear spectrum of gamma rays, typical. This is when you lose a gamma from annihilation, so we call it a single escape, and then you lose both gammas from annihilation of the positron, so this is a double escape. So when you study a resonance, and the best is to have a thick target, and then you get such a step function, and this is the function that you use to fit this step function, and this is the resonance strength. This is then directly related to the cross-section. So by determining the resonance strength, then you can, from the cross-section, determine the electron screening. And this is our result for these two foils, soft palladium and hard palladium. So you could say, okay, this is all the same, but it's not. One contains 50% less hydrogen, meaning that the resonance strength in that case is 50% higher. So that's how we determine this electron screening potential. What is also important is that the hydrogen distribution in the foil is fairly flat, so this is important for further analysis. And that's when we load the deuterium in the target, then we use this reaction, helium-3 on deuterium, and we measure this 12 MeV protons. And that's, if we change then the beam energy, then we can get the depth profile in the target. So here is what, for example, happens in a titanium target. So this is after, I think, 1 day of loading with the ion gun at about 400 microamps at 3.5 kilovolts. And then that's the blue one. Then we clean the surface mechanically so that we get all the deuterium on the surface. That's the red one. And then after the experiment, we have the black curve. So that it's important that the distribution doesn't change during the experiment. So we can, using this distribution, we can then determine the electron screening potential. Then, we wanted to study the reaction between fluorine and deuterium. And of course, before we started, this cross-section was not known, so we had to measure it. And we measured it in normal kinematics. So we went to Garching, where they have the deuterium beam, and measured the cross-section, how we measured it. This reaction produces fluorine-20, which is radioactive. Then this fluorine-20 decays and emits in almost all the decays, emits this gamma ray of here, this one, 1634 keV. And that's the characteristic gamma ray to determine the cross-section. So we measure this characteristic gamma ray, change the beam energy, and at each energy we count the number, and we can determine the cross-section. So these red points are our results. So by knowing then the cross-section, the bare cross-section, then we could study the inverse kinematics reaction, where we expect electron screening. So this is what happens. We determine in hard palladium, we determined 18.2 keV for the electron screening potential. The adiabatic limit is 2.2 keV. And on the other hand, in soft palladium, we didn't get any electron screening, which also says that we deduced the cross-section well in normal kinematics. So just by changing the structure of the palladium target, we increased this electron screening potential to more than an order of magnitude, or almost an order of magnitude above the adiabatic limit. Then to check a little bit on the Z dependence of electron screening, we also studied lithium on protons in inverse kinematics. So now we knew that in the soft palladium, there was no electron screening. We just divided the yields of the two targets, and then we could determine the electron screening potential in hard palladium, which is 2.9 keV above almost, okay, thanks. More than an order of magnitude, again, above the adiabatic limit. Then to try to understand the difference between this hard palladium and soft palladium, what happens to the protons in there, we studied nuclear magnetic resonance on both soft palladium and hard palladium. So what in nuclear magnetic resonance, the night shift tells you the electron density around your protons. And you see that there is a difference. And we deduced with some other, some older calculations, we deduced that the electron density in the case of hard palladium has to be much higher than in the case of soft palladium, the electron density around the proton. So a little effort to try to explain this is, you know, if you have this is the normal FCC lattice, and then this red hydrogen sits at what we call octahedral site in the middle of this cube. But then when you remove one palladium from the lattice, this hydrogen is pulled away towards this vacancy. And there are more ways to try to do that, either radiation damage. We tried in the past, as Natalia said, stretching the palladium. And okay, in this case, it was cold rolling of palladium that probably produced, I mean, definitely there was some stress in this target. You saw that it's all deformed. And then could produce, for example, such vacancies. Also some other defects which are probably responsible for large electron screening. So these are somehow our final results, what we have so far. Different targets. The same reaction that I was explaining before. We shoot fluorine-19 on deuterium, implant it in different targets. We had zirconium, thick titanium, powder titanium, we had a thin titanium, soft palladium, hard palladium. And already these are the depth distribution. This tells you already something about what happens with deuterium in different targets. So in these cases where you had high diffusion, the deuterium is almost flat. Because it's all over the target. But in the cases where we had to implant, the deuterium, it doesn't diffuse, so it's only present until a certain depth in the target. So this was the case of zirconium, thick titanium, And this thin titanium was made such that we evaporated titanium onto tantalum backing and then implanted it, and you can see that it's only, deuterium is only in the titanium layer, not in the tantalum layer. So we got then different results for electron screening. Except for this soft palladium, they are all above electron screening. Oh yeah, this powder titanium, this was produced in Dresden. They heated this powder to 700 degrees and then put it in a hydrogen atmosphere. So then it had time to diffuse. So this one is also inconclusive, so it could also be no electron screening. But you can see that different ways of preparing the targets, they give you different results. The most effort we spent on palladium, we don't know about titanium, why we have different results in different titanium targets. So this is the last one that I wanted to show. There should be a movie. No. No, it doesn't work. Oh, it does. Okay. So we tried to do some progress on the theoretical side as well. So trying to explain these large electron screening potentials that we measure. So the idea is to look at hydrogen molecular ion and then calculate the electron wave function within the hydrogen molecular ion. And this, then we took the probability to find the electron in between the two protons or deuterons, and then multiplied the Coulomb barrier. I mean, we assumed that once, if the electron is between the two, then the screening is complete, so you have no Coulomb barrier. So then we changed the Coulomb barrier by multiplying it with the probability for, for the electron to be outside of, that it's not in between the proton and the neutron, the other proton. And then with this modified Coulomb barrier, we are now trying to calculate the tunneling probability, and I hope we are very close to getting the result. If my student calculates it while I'm here, then we are done. So I have high hopes that we will get these high electron screening potentials with this model. So thanks.
Any question? Yes, Bill?
I just wanted to say that in the case of muon-catalyzed PD reaction, you do indeed get a muon carrying off almost all the energy, and that obviously is not a hot fusion reaction by definition. But that only, the percentage of that channel is about 15%. 85% is standard hot fusion with a gamma ray.
Yeah, but it's not the same as hot fusion.
It's not quite the same, very similar. No. You get a gamma ray, or you get or the muon can carry off the energy. No neutron. P plus D. Oh, well, okay. Exceptionally.
Okay. Another question?
Not necessarily to do with your research, but is the electrical resistivity of work-hardened palladium different to that of soft palladium?
We haven't checked. These are these big faults, so it's not straightforward to measure resistivity on that. But we haven't tried. We are happy with weighing the faults, so we know how much is in.
So, another question? Yes, here.
This picture you show, what is the de Broglie wavelength of your particle?
Yeah, well, the energies are the energy of the resonance is 323 in the center of mass. So you can calculate this.
Yeah, but is it localized over one particle or 2, 3, 4 lattice?
No, it's one.
You calculated it?
Yeah, yeah.
Oh, okay.
Okay, thank you very much. And then we have our next speaker is Francesco Celani. So you have 10 minutes only this time? No, 10 minutes.
Okay. Hello. My talk. Okay, go. Hello. Doesn't work. Indietro. Ok, vale? Questa e questa, sopra sotto. Ah, questa e questa. Okay, my talk was mostly presented during the press conference in the United States, but luckily we analyzed deeply one effect that we don't have time to study in such conference. So the point is, most published in the press conference, but we are able to have the proof that modification of Constantan has the effect to increase some performance useful to get HSIT. And moreover, we have some evidence that one possible location of anomalous effect are related to the superabundant vacancy phenomena, studied at the beginning from Professor Fukai in Japan, and recently from Professor Stacker in the United States. Other point of our talk was to find a simple approach to get an anomalous effect without using pulsing that is difficult for normal people. Again, we reconfirm that the main parameters, the main effect that promote the anomalous effect is the flux of hydrogen or deuterium along the materials. The flux phenomena was discovered from Professor Fralick in NASA in 1989, the beginning of the cold fusion, but unfortunately these data were not made public for several reasons. And other points is in addendum I had one paper of my collaborator about new model, but it will be presented in the Italian version of this conference 2 days later. Motivation was to reproduce the anomalous effect in a simple way. We have done a lot of work using pulse. We demonstrate that a pulse condition is able to promote fast loading of the material and effect, but it's really difficult, and several people is not useful for common people, for normal students, or so on, industry. So we have found that applying for very long time DC current at high at high temperature is equivalent to have pulsing for short time. It means 5 hours in pulsing is equivalent more or less to 10 days in DC condition. Just to have an idea. The experimental setup was the same we are using from several years. Is just a coaxial, inverse coaxial coil. This one, the coil, put inside a glass tube. At the inner, there is iron counter electrode. Very simple setup. It seems maybe too much simple, but it works properly because you need to make several experiments in a short time. If you use conventional flow calorimetry, we need for one measurement 6 hours, 8 hours. So it's too long for us. So we can make 2 experiments maximum in the day. Using dispersion calorimeter, if we make proper calibration, it's possible to make 1 experiment in half hour. So a factor, quality factor more than 10. Schematic of our coil is the Constantan is put inside this glassy sheet. It is details. So now no time to go. Anyway, you can watch deeply. The experiment is 2 phases. One is the preparation procedure, by mostly chemical, physical procedure. The other, the activation. For the preparation, we have enough experience and we can make quite easily. Most difficult is activation. So means we have to put the hydrogen in some specific position of the lattice, for the Constantan, to have the effect. So for this point, we think even the cold working effect discovered from Japanese people at the beginning can make a rule, but we have to promote locally the cold working, similar to cold working, so the pulse procedure make the same effect, or very long time at high temperature. The pulsing is quite powerful. We have a power density as large as 10 kilowatt for gram of Constantan. And the pulse duration was about 10 microseconds. But it's difficult, so we used DC procedure for very long time. Now I skip several because the time is short. And okay. It's the experiment about the chest heat normalized. We use as a reference the experiment under hydrogen. Input power, and in this plot, the quality factor apart chest heat, the resistance ratio of Constantan. At the beginning, it is the shape in hydrogen of resistance ratio. little bit increase, but little bit about 4-5% up to 800 degree. After hydrogen absorption, there is a decreasing of the resistance because the hydrogen has the ability to reduce the resistivity of the material, and we found such effect systematically. So we have a cross-check about the chest heat and resistance ratio. As we go to a longer time, the effect is increased. Now, some simplification results. In this experiment, we want to check if we were able to restart the material after we make for some hours vacuum at high temperature, and we succeed partially. So it means if you make some strong treatment to the material, not always is possible to have the original value of good. So example, the best was experiment number 4, where we make some vacuum treatments for a short time, the efficiency decrease. So the constant time as memory, remember, memory of what we have done. So it makes the experiment very difficult to understand and to control. Moreover, we have lucky the first time we were able to demonstrate that using deuterium with constant time, the HS heat is larger in respect to hydrogen. Now, in all our previous experiments since 2011 to 12, when we move from hydrogen to deuterium, we have the HS heat almost disappear or even negative. So after 1 day, 2 days, we move to another kind of experiment. But the point is, at time, we didn't wait enough long time. We want to get a new result as soon as possible, so we didn't wait enough time under deuterium. This time we wait enough, the experiment of December, 3 months. So the first experiment with hydrogen, after several days, we get the chest heat number 1. So the maximum is about 120-23 watt of input power, and the effect was about 2 watts. When after waiting several days, several experiments, it increased up to 5 watt input of watt HS power. When we move to deuterium, it increased more to about 6 watts from 5 to 6. And this is the most interesting experiment. This experiment was done when before we have for a long time the loading at very high temperature. This make changing of the lattice of the constant time. And the changing means the composition. As I told before, we think this effect because some hydrogen is loaded, is locked in some specific point of the lattice. The people call superabundant vacancy, where it's concentrated. So we want in such kind of experiment previous. We got good results with deuterium, so we want to restart again and reproduce the results. So it was almost very difficult to deload fully the deuterium. So we wait we make high power for a long time, 16 hours. It it was the first time. But we get like a accident. The point is, because we work with the constant current, if the resistance increase, the power increase, so the temperature of the wire increase. Usually, when we make the loading by vacuum, we watch what is going to avoid too much temperature. This time it seems stable for 1 or 2 hours at the beginning, so we leave the system overnight. But when the morning we have seen the temperature arrive up to 860 degrees, starting from 680, so very large increasing. Oh, sorry. The reason of so large increasing temperature are two. One, we detected large increasing of resistance. The second one, because the material change, we have large resistivity thermal coefficients. So two effects at the same direction. So the effect is that this is resistance ratio for the pure constant at the beginning. It's very, very stable. When we load some hydrogen, several cycles, or deuterium, there is some increasing, but not so much, because it's counteracted from the effect of loading. But when before, for 15 hours, at very high temperature, we have a jump of the resistance ratio from about 1.004 to about 1.25, and moreover, a very large temperature coefficients. So it was the key of the understanding. But remember, this was just an accident. We don't want this one. In the evening, we wait here at all in this condition, 50 watt, at about 90 watt, and all was regular, but it was at this point, so we don't worry. But slowly, by itself, it's increasing. And that we have proof what happened when we work at constant current. The voltage drop along the wire increase. So this is good for to get anomalous effect. This was normal while the special after a long time changing, 15 hours. So at the same power, we have over then about 20 voltage increasing at the same power, and this make effect, voltage effect along the wire, and again the temperature, the normal temperature effects of the wire, this one, and this is for after vacuum treatment. But this curve is extremely important, because with the same internal temperature, with helium at the beginning or the hydrogen, we have 0 power with helium at the same temperature, or about 9 watts. So it means the gas effect is a key rule. So with helium, the thermal conductivity is lower than deuterium, means at the same power we have high temperature. This is about 800 in this kind of experiment. With deuterium, conductivity is higher, so we have same temperature, but helium, no power, it's calibration, zero by definition, with deuterium 9 watts. So this is a demonstration of the effect of the deuterium stored inside the lattice. Conclusion, the flux, again, according to us, is the key parameter. So as fast as possible. But the flux means some energy added to move the gas inside. So we have to minimize the extra energy needed to get flux. And we get information just by chance that using vacuum it's possible to change the bulk composition of the material. And so it means the copper was depleted. We have proof of this point. So there is some optimal composition of the constantan that increase the HS power, optimal amount of copper. Anyway, some pieces of the wire has to be constantan because it allows decomposition dissociation of hydrogen from molecular to atomic state. So it has to be both material at the same time. Okay, this is just an invitation to attend next meeting from Mr. Cereoni, our colleagues. About acknowledgement, we collaborate with Muterucci company in Italy from over 11 years. We have a collaboration with Italy, France about construction of the glassy sheet. We get some support of this new company, but it's just follow-up of another that they give from about 5 years some money to survive and attend the conference. And a special thanks to our Clean Academy AHME project. Obviously, we say that all the mistake of ours are our responsibility, all the good of the clean project. And, okay, so.
Francesco, you did very well. I'm very impressed. You had 10 minutes and you took 20. That's okay.
This is a true miracle.
Okay, now, any question? Because we have lunch after that? Yeah,
okay.
One. Bob, you have to make it short. But don't speak fast.
Hey, don't speak fast. I am Italian, don't forget.
When I was doing replications with MFMP of your cells back in the 2012 to 2013 period, my one regret is I didn't get to look at different excitation modes from the outside. I discussed with you about using piezo sound-induced vibration, but I don't know whether you explored that, but I'd also consider high-frequency oscillation through a solenoid mounted around the outside of the cell, but at very, very, very low power levels, almost negligible, but to have that AC oscillation. And then lastly, to have an electric field in excess of 500 volts across the cell static.
Maybe. Okay.
Have you tried any of those?
Okay, we've done several experiments using pulse condition. The pulse enhance the effect for several reasons. One is local concentration. One is local extra heat. So there are several effects altogether. But it's complicated. So the people say, oh, we cannot understand. And we move back to DC. So this is the point. But we found that just living for a long time, 1 week, 2 weeks, we see we have a similar effect with pulse, but at a lower intensity. So the origin is the same.
But the pulse is directly through the wire.
Yeah,
I'm
yeah.
referring to a solenoid around the apparatus.
But there is some electromagnetic effect, so it's very, very complicated. So, okay, that's the point.
Okay, thank you very much. Last question before lunch.
Okay, I would like to ask you about the hydrogen density in your sample.
Yes.
If you compare hydrogen to the deuterium, there is this similar densities you have there?
I don't know. We don't have possibility to measure. We just observe it. Okay, with the fixed experiment, there is not so much difference about hydrogen and deuterium. But if we think about the local concentration, like superabundant vacancy, it can make the effects. But we don't have instrumentation to look for such kind of effect. Okay. In the second experiment after vacuum, it was a very large changing of the material. So we make 1 week, 1 full week under high temperature, because we want to reduce the temperature, the resistance. But it was a very little effect. So it means it was almost stable changing of the material, and it was the main factor. Yeah. But luckily, with this changing, the HSC increasing. So now we open our eyes to modify the composition. Maybe similar effect can was discovered from Japan group. So they make copper nickel, and with pure nickel no effect. So really is a material effect.
Mm-hmm. So as I understand, you have a very nice effect in the case of deuterium gas because of waiting for a longer time.
Yes.
But we understand that one of the key parameter that can control this kind of heat excess is the fusion.
Yes,
effect.
diffusion.
In the case
I agree.
In the case of deuterium, the diffusion coefficient is much lower than the
Yes, I agree.
So
we worry that we cannot work well. So when we get a negative effect in some way, at the beginning of experiments, using the deuterium, say, okay, the speed is lower, diffusion speed is lower, so it's normal to get nothing. But this time, because we get some positive results with the deuterium, we say, okay, we accumulate good results, now we can try something funny. If the wire break, no problem. But we just were lucky. So we made what before we avoided. So it means the possibility in this field are very large. So not short. Okay.
Because people are hungry. Now I'd like to thank Francesco and all the speakers of this morning session. And we have lunch at the Roseto Ristorante somewhere downstairs. See you at 2:30? Yeah. 2:30 we recover. No.